So now let's talk about the Cartesian product of countable sets. So let's start by defining the Cartesian product. Let's let x and y be sets. Then the Cartesian product is written x cross y. This is the set of all ordered pairs x comma y, such that little x is in big X and y is in big Y. Notice that I wrote ordered pair with round parentheses instead of squiggly braces. This isn't the set little x, little y. The ordered pair 1, 2 and the ordered pair 2, 1 are different from each other. So it's like a set, but we keep track of which one is first, which one is second, and you're allowed to repeat yourself. You know if you're repeating yourself. And you can also write down the Cartesian product of 3 sets. That would be ordered triples, x comma y comma z, and so on. And now here is a proposition that might be somewhat surprising. And that's that if you take the natural numbers and you take the Cartesian product of the natural numbers with itself, that is countable. Now we saw before that the integers are countable. There are twice as many integers as natural numbers, but in some sense there's the same number. And here's the same thing. Here we've got effectively infinitely times as many. So here is how we go about proving that. So I'm going to write the Cartesian product in it like this. So here is 1 comma 1, here is 1 comma 2, here is 1 comma 3, here is 1 comma 4, and so on. So we go off infinitely far in both directions. And then what we're going to do is we're going to trace a path through this grid that looks like this. We start here at 1, 1. We go to 1, 2, then to 2, 1, down to 3, 1, up to 2, 2, to 1, 3, over to 1, 4. Reverse our diagonal line down to, I guess I didn't write it down, but we'd go to 5, 1. And notice this path is eventually going to get everything, and you can traverse it one at a time. So we're going to let f of 1 be the pair 1, 1. F of 2 is going to be the pair 1, 2. F of 3 is 2, 1. F of 4 is 3, 1. F of 5 is 2, 2. F of 6 is 1, 3, and so on. And the idea is, so we've got, so here's f of 1, so here's f of 1, f of 2, f of 3, f of 4, f of 5, f of 6, f of 7, f of 8, f of 9, f of 10, f of 11, f of 12, f of 13, f of 14, f of 15, so on. the idea is, and you can, if you put your mind to it, write down a nice formula for f of n, but it's really more trouble than it's worth. So then this is really getting you the idea. Then f goes from the natural numbers to the natural numbers Cartesian product with itself. That is surjective. In fact, it's even bijective. So n cross n, that is countable. Next proposition says that it's not just the natural numbers cross the natural numbers. Let x and y be any two countable sets. And then the Cartesian product of x and y is also countable. And then to prove this, let's let K be a mapping from n to the Cartesian product of n with itself, be a surjection, bijection, whichever you prefer. And we saw in the last proposition that K exists. Let B, C be subsets of the natural numbers. And we're going to let G goes from B to X, and H goes from C to Y be also bijections. And this is where we're using the fact that X and Y are countable. All that gives us that G and B and H and C exist. So if n is a natural number, then K of n, that's in our Cartesian product. So that's some number K1 of n, some other number K2 of n. So we can define two functions, K1 and K2. So K1 goes from the natural numbers to itself. K2 goes from the natural numbers to itself, such that K of n is K1 of n, K2 of n, for all natural numbers n. K1 and K2 are going to be surjective. They aren't going to be one-to-one, and because you need to repeat yourself, but they are at least functions. And since K is on to K1 and K2 also have to be on to. So let's let A be the set of all n in n such that k1 of n is in B, k2 of n is in C. This is k1 inverse of B intersect k2 inverse of C. So the idea is every point in A, you apply k1, you end up in B, you apply k2, you end up in C. And let's let F going from A to X cross Y be given by F of n. That's going to be G of K1 of n, and then H of K2 of n. All right, so then G is obviously a function from A, which is a set of natural numbers, into the Cartesian product X cross Y. And then if X, Y is in our Cartesian product, X cross Y, then, well, G is supposed to be onto, H is supposed to be onto, X is some G of K1, Y is H of K2 for some numbers K1 in B, and then K2 is in C. And that's true because G, H are surjections. All right, and then K1, K2 is in B, and then K1 and K2 are in, K1 is in B, K2 is in C. Let N and then K1, K2 is in N cross N. It's an ordered pair whose elements are both natural numbers. That means it's K of something. So our N has to exist. And K1 is in B, K2 is in C. So our N is in A because K1 of N is K1 is in B, K2 of N is K2 is in C, and F of N is, remember, that's G of K1 of N, H of K2 of N, but that's G of K1, H of K2 is XY. So F going from A to X cross Y, that is surjective. And so now we've got a surjective function from a subset of the natural numbers onto our Cartesian product. So, but a proposition 1.5.3, X cross Y is countable. And that is what we were trying to prove. So the theme of this video is definitely weird sets that seem much bigger than the natural numbers that are nonetheless countable. So in particular, the set of all rational numbers, Q, is countable. And then the proof of that is that Z, the integers are countable, the natural numbers obviously are countable, so by the previous proposition, Z cross N is countable. And it's example 1.5.2b and proposition 1.5.4. And then if you let f of z n be z divided by n, then f from z cross n to q, that it is surjective. It's not one-to-one. F of 1, 2 is the same as f of 2, 4 is the same as 3, 6, but surjective is all we need. So that was proposition 1.5.3. Q is countable. All right. Another corollary. If X, Y, and Z are all countable, so is X Cartesian product with Y Cartesian product with Z. And the proof is that if you just let f of, we saw that X cross Y is countable. So then if you take X Cartesian product with Y, and then you take the Cartesian product of that with Z, that is countable. And then Cartesian products aren't quite associative. X cross Y cross Z isn't quite equal to X cross Y cross Z. Let f of and then xy comma z be the triple x comma y comma z. So f is just a function that forgets about some parentheses. F is bijective. So X Cartesian product Y Cartesian product Z, that's the set of all ordered triples X, Y, Z. That is countable. And I'm not going to write it down, the statements in your book, but you don't have to stop at 3, X cross Y cross Z cross W, X cross Y cross Z cross W cross U. Any finite number of countable sets, you can take the Cartesian product and get a countable set. quick proposition because this is going to be helpful. I've got two more sets that I want to show you that look like they ought to be too big to be countable but aren't. And I think having this proposition in front of us will make it a little easier to prove that. Let's let X be non-empty and countable. And then we know that means there's a bijection between X and a subset of the natural numbers, but I'm getting tired of messing around with subsets, so the conclusion is that then there exists a function from, let's say, all the natural numbers onto X that is surjective. It's a homework problem or possibly an exam problem that if F is countably infinite, then there's actually a bijection from X to all the natural numbers. But if X is a finite set, the best you're going to get is a surjection. So the proof is pretty quick. Let's let A be a subset of the natural numbers, and we've already used the letter F, so let's let F twiddle be a function from A to X, B. By assumption, there is such a subset A and such a function F that is a bijection. And then X is not empty, so we're going to pick one X naught in X. And we're going to define the function F of n. This is going to be a piecewise defined function. It is going to be F twiddle of n if n is in A, and it's going to be X naught otherwise. So then clearly F is a surjection. F twiddle is a surjection. F twiddle gives you everything, and R and just this throwing in everything else isn't going to make you stop being onto. So here's another big set that is nonetheless countable, 1.5.7. Let's let X be the union of countably many sets, and suppose that each xn is countable. Then X is countable. And then to prove that, let's go ahead and assume that the xn's, none of them is empty. If one of them is empty, we can and just throw it out. It doesn't contribute anything to our union. Let's let gn go from the natural numbers to xn be a surjection. And let's let F go from the natural numbers Cartesian product with itself to X be given by F of nk is G sub n of k, then F is surjective. If you pick an element of X, it's got to be in one of the xn's, and Gn is surjective onto Xn, so Gn of k is going to give you whatever element you picked for some k, and the natural numbers cross themselves. That is a countable set. And so by proposition 1.5.3, X is countable. And here is a corollary to this. This is corollary 1.5.8. And this says that the set of all finite subsets of the natural numbers, that is countable. And this set, this collection, the set contains the empty set, all the singleton sets, all the pairs, all the triplets, all the quadruplets, and so on. So this is a big set. It's got the natural numbers, the pairs, the triplets, everything you want. And nonetheless, it is countable, and here's the proof of that. Let's let Sn be the set of all subsets of going up to n. Sn contains 2 to the n elements. This is a little bit confusing because now the elements of the set Sn are themselves sets. But so just be careful. So each set either does or does not contain 1, either does or does not contain 2, either does or does not contain 3, up to does or does not contain n. So we can write this as a list. You've got the empty set that contains nothing. You've got the set that contains 1. Then you've got the set that contains 2. the set that contains 1 and 2. And then you can double that by throwing 3 in. And then you can double that. So you see we've got two subsets of 2 sets that only contain 1, the empty set and 1. When you allow yourself 2, you get twice as many. You basically throw 2 into each of those. Then when you allow 3, you get twice as many. You get 4 more, you throw 3 into each of those. Not going to write it out, but allowing 4 would get twice as many again. So the upshot is that Sn contains 2 to the n elements, so Sn is finite, so Sn is countable. And then the set of all finite subsets of n, that's just the union of the Sns, is countable. So we've seen a whole lot of sets that are countable. So here we're going to see for the first time a set that is not countable. And this is the set of all subsets of n. This is sometimes written as 2 to the power of n, power set of n, because for each natural number you can decide whether or not you want to include it, and that is not countable. All right, and let me go ahead and write out a couple of the things in 2 to the n. That's, we've got our empty set and our singletons and our doubletons and our tripletons. So we've got all our finite sets from before. But we've also got the infinite sets. We've got the natural numbers, the set of all odd numbers, the set of all the perfect squares, the set of all the primes, and so on and so forth. So now we're allowing ourselves the infinite sets as well as the finite sets. And the claim here is that throwing in the infinite sets, that is enough to make this uncountable. And so let's go ahead and prove this. Let's let f be a function whose domain is n and whose range is the power set, the output 2 to the n. So perhaps f of 1 is the empty set, perhaps f of 2 is the singleton set 7, f of 3 is the doubleton 4, 5, f of 4 is 1, 2, 3, f of 5 is all the natural numbers, f of 6 is the odd numbers, f of 7 is the squares, and so on. So it's just any function like that. So now we're going to define a set S like this. Let's let S be the set of all natural numbers n such that n is not in f of n. Remember, f of n is a set. So, for example, let's suppose, say, f of 1 is the empty set, and then f of 2 is the singleton set at 1. Let's say f of 3. Let's make that the doubleton set 2, 3. Let's say f of 4 is all the natural numbers. F of 5 is the set of all the perfect squares. F of 6 is the set of all odd numbers. F of 7 is all the prime numbers. And so on and so forth. And then we go through and we say, okay, f of 1 is not in the empty set, and 2 is not in the singleton set whose only element is 1. But 3 certainly is in the set 2, 3, and 4 is in the natural numbers. 5 is not a perfect square. 6 is not odd. 7 is prime. And so our S is going to be, it's going to have 1 in it. It's going to have 2 in it. It's not going to have 3 or 4. It's going to have 5. It's going to have 6. It's not going to have 7, but so on like that. But the point is, if you've got a function f like this, then you can construct this set S. You can come up with an S that works. This set S exists. And then here is my claim, is that f of n is not equal to S for any natural number n. So we're claiming that f is not surjective. And then the proof of claim this isn't the proof of the whole proposition, just a little subclaim in the middle of it, is that if n is in S, then by definition of n is not in f of n, and is in S and is not in f of n, so f of n can't equal S for any n that is in S. And conversely, if n is not in S, then by definition of S, n is in f of n. So f of n cannot be equal to S in this case either. So f of n is not equal to S for any natural number n. And thus, f going from n to the power set 2 to the n is not surjective. But f was arbitrary. All we've used is the fact that f is a function whose domain is n and whose range is 2 to the n. And we've shown that it is not surjective. So no function from the natural numbers to its power set can be surjective. If it was, we'd be able to construct this at S that it doesn't hit, and that can't happen. But you saw before, we saw proposition, so the unnumbered proposition just before, or proposition 1.5.7, we saw that if you're countable, you've got a surjection from the natural numbers. But if 2 to the n were countable, there would have to be a surjection whose domain is n and whose range is the power set to the n, and that is part 3 of this video. And so 2 to the n is not countable.